Hi and welcome to my presentation on zero CPU collection with direct telemetry access. Network telemetry is fundamentally about extracting information from the network, and the current state-of-the-art sends information directly from individual switches towards central collection. And this can allow for very efficient centralized queries and controller reactivity. But networks can easily grow into tens of thousands of individual switches and much larger still in hyperscale networks. And each switch still sends the information towards centralized collection. And this puts a very high load on collection. And this is recognized to be a big problem. And Alibaba reported in last year's SIGCOMM that a single switch might send several millions of network anomaly reports per second, which of course is incredibly expensive for centralized collection at these scales. And we might ideally want to extract even more information from the network than just these anomalies. For example, we might want to do per-flow path tracing or extracting congestions, flow sizes, and so on. And collection easily grows incredibly expensive. We have benchmarked two different systems that are commonly used for telemetry data collection, and we split the work into packet I/O and actual storage cycles where we write the data in a queryable way to memory. So we started checking out Apache Kafka, which is a well-known tool for processing streaming data, but it's really not designed for high-speed telemetry collection and was really struggling at these scales and rates. So we instead went with what we see as the current state-of-the-art, which is Conflow. Conflow is published in NSTI 2019 and was built specifically for high-speed telemetry collection, which they approached by designing their own very optimized stack. But the CPU is still struggling, and the issue is not just packet I/O, because as you can see, that's just a very tiny sliver of the total work. And in Conflow, we need more than 100 times as much work for storage as we do for packet I/O. So the CPU is really struggling with telemetry storage and especially insertion into queryable memory. Our ideal design therefore doesn't really use the CPU for this work, so we don't want the CPU to do the storage work, and this includes no centralized data organization or collision handling inside of the server processor. And we also want the design to be scalable with low overheads, including a very low level of on-switch statefulness, because as we all know, that's incredibly costly, especially at these scales. And preferably very low level of inter-switch collaboration to keep it very scalable with low overheads. And we want the design to be fully in the data plane, both for a reduced footprint and to be able to handle data as it pop in and out at data plane timescales. But we also should not forget about the main point behind telemetry collection, which is to allow very efficient centralized queryability. We don't want to force an operator to query individual switches for specific information. We want data to be already there central for very efficient and fast processing. Alright, we have incredible rates of data from the network that we want written to server memory. And this is pretty much exactly what RDMA is designed for. RDMA is a technique to remotely access memory of another server through the network, and these operations are triggered by network packets on the network card, and the network card directly accesses memory through DMA and thereby directly bypassing the server CPU. And current generation RDMA can perform literally hundreds of millions of memory reads and writes per second, which is a big improvement on collection speeds, especially given that we also free up the CPU to do other potentially more useful work. But there is an issue, and one-sided RDMA especially imposes several restrictions in our design. And one of the most relevant ones is that it totally lacks centralized pre-processing of memory accesses. And a packet therefore specifies a location for a value, and exactly where that value will be written on the server. And we will just have to design around that limitation. We have redesigned telemetry collection to fit the restrictions of RDMA through a fundamentally key value based design. All telemetry data in a network has a unique identifier, it's the telemetry key. And when a switch wants to report some piece of telemetry data, then it does it under that specific key. And we found that most telemetry scenarios can be translated into a key value representation. One example is if we want to do just any per flow per switch measurement. Let's say we want to do some path tracing or maybe just any INT postcarding. In this case, the switch would report this information with the key as a concatenation of the flow 5 tuple together with the switch ID. And when an operator wants to extract information about, let's say, flow A at switch 1, then it just requests that key and extracts that piece of telemetry data. Keys are mapped to their final source locations through global hash functions. So when a switch wants to report a piece of telemetry data, then it hashes this telemetry key into a collection server and a memory address inside of that server. And it will then generate an RDMA packet to write this information into the memory of that server. And an operator can then simply perform these same hashes and then read and extract the telemetry data from memory at that server. And as you can see, so far the design is very simple. It's pretty much the same as a basic hash table. But there's a problem here. Hashes can collide, and in our case this would result in overwritten data. But we want our design to be near stateless with no inter-switch collaborations, and we want shared global memory where every switch writes to the same set of memory addresses. So, hash collisions and data overwrites are unavoidable, right? Well, maybe. But let's try to avoid inter-switch interference entirely by instead dedicating memory at central collection for each individual switch. What would happen in that case? Well, of course we wouldn't really have to think about collisions from other switches because we have dedicated exclusive access to a piece of memory, but how would we handle collisions from within each switch? And we don't really believe that stateful solutions here are feasible, both due to the amount of required memory and the increased algorithmic complexity. Because a switch might have to handle literally hundreds of thousands of keys just for per flow telemetry queries. And we would greatly increase the on-switch footprint of our design by going down this approach. And we again really shouldn't forget about the main point behind telemetry collection, which is allowing efficient queryability. And this approach would require an operator to beforehand know where to look for data before it can be queried, and therefore know which switch wrote that data. And then it would also have to figure out where that switch finally wrote that data as well, according to some internal collision mitigating algorithm. And this would pretty much just increase the overheads overall of the design. We have designed a stateless solution where all switches share the same centralized memory regions. And address collisions are partially tolerated by having switches write the data into several storage locations. And unfortunately, RDMA only supports writing to a single address per packet, and would therefore have to generate several RDMA packets to store this redundancy in telemetry storage. And an operator can now just check these memory addresses until they find a valid version of the data, and it can discard invalid data through built-in checksumming and plurality voting. Okay, so let's put these pieces together into a full design, which we call Dart. Recall that we have two distinct components. We have querying on the left and we have reporting on the right. A switch has some telemetry data that it wants to report. It hashes the accompanied key into a set of storage locations and uses this information together with preloaded lookup tables to craft RDMA packets. These packets are sent to the collector, which writes this information to memory. And the data is now available for operator queries. So we now want to query this data. The operator states a telemetry query which is sent to the collector. The collector translates this query into a set of keys, which is reads from memory and processes this information. Invalid data is discarded and a query response is compiled and sent back to the operator. And that's pretty much it. That's a brief overview of Dart. Alright, the last slide. What's our goal and what are we aiming for? First, we want to generalize beyond key value queries. For example, how do we query against aggregated network states when there's not some obvious key that can be used to synchronize the network? Let's say we want to extract a list of the top 10 heaviest flows inside of the network. How can we support those kinds of queries? And how do we more generally query the unknown? Let's say that an operator just wants to iterate over the data. How can it do that if it doesn't already know the keys that are queryable? And how do we best enable immediate controller reactivity? For example, how do we poke the controller to ensure real-time controller response to events? Because after all, this is one of the main use cases of telemetry collection. And we are looking into designing a tailored RDMA especially for telemetry. And this could include new primitives, for example, a multi-write primitive to write the redundancies with just a single packet. And this would greatly reduce the network overheads of our design. And a tailored RDMA could also remove the need for a super reliable network. And I think this is one of the biggest points here. And our main vision for the full paper for our future is to design a transport protocol for telemetry data. We want direct telemetry access to be just one component in a full telemetry system where it can be a plug-and-play transport protocol for whichever measurement backend and controller processing framework that you want. And that's it. Thank you.